Now that we have wrapped up our first example, let's go ahead and take a look at the composite section, which is the second type of SI torsion. And we're going to just dive right into a example. We're going to have a section that looks something like this. So there's our composite. Now, a lot of times when we used to draw that, that could also mean it was hollow. But that is not this interpretation. Instead, we have the steel core, just like an apple core. It's the one on the center. And then here we have the aluminum shell. So core shell is a typical phrasing. So a core shell is a phrasing that's commonly used in the business. And in this case, we have these two different types of material, and there's going to be a torque that's going to be applied this way. And that is going to be equal to 4 kilonewton meters. And for whatever reason, this thing is really long. This is 25 meters. Who knows what it's being used for? And we have the geometry set up for us. And in this case, all of the input data that we've got are going to be in terms of millimeters. So we'll have the outer, let me see, I'll try to draw these over here. The outer diameter of the outer shell is going to be 72 millimeters. And then the inner, let's put the inner over here. That's going to be equal to 54. And we have the values of G for the aluminum. Then G is going to be equal to 27 GPa. And for the steel, G is equal to 77 GPa. So about a factor of 3 or so, that's about right. Aluminum is typically softer than steel, both in terms of the elastic and the shear moduli. And so this is a classic problem, and it asks basically to find what are the maximum shear stresses in both. So we'll write it like this. The max shear stress in the aluminum, the max shear stress in the steel, and then we also want to find out theta where the twist is applied. Let's go ahead and call these A and B. So theta of A, which is basically the twist of A relative to the fixed support, which is going to be our point B. But that's our problem setup. Now, the way that this problem is appearing is basically saying that there's a torque of 4 and the core, the steel core resists part and the aluminum resists apart. But we don't know how much that is. Do they each take 2? Is it 3 and 1 or 1 and 3? And we're not going to know that before the fact. So we still have to do our big 3. So the first is going to be statics. The nice thing about these problems is the statics is borderline trivial. This just says that the applied load of 4 has to be balanced by the torque in the aluminum and the torque in the steel. I'm just going to use one letter for these. So statics for composites is almost always really, really easy. So always very straightforward. It's just saying that the applied torque, part of it's going in one solid, part of it's going into the other solid. So you don't have to do anything else. There's no internal that you have to do because those values are the internal values. Another way of viewing it, if you look at a picture of what's going on inside, is that you have the resistance of the torque is part of it's going this way, part of it's going this way, depending on our viewpoint now. So we're going to have the torque then in the aluminum shell, and then we're going to have the torque in the steel core. So part of it goes into each one, and the resultants are basically summing up to those particular values. Don't worry about the directions here. It depends on how we're drawing this thing. All right, so the statics is very straightforward. The next is going to be the stress-strain law, and that's going to be that the total twist of our aluminum section. So theta of the, I guess maybe I should put in AL and ST because A is our point A. So let's go ahead and change that. So theta of the aluminum then is going to be equal to the torque in the aluminum times the length of the aluminum divided by J of the aluminum and G of the aluminum. So it's almost pretending like there's only that segment. So we're going to go ahead and put in the values that we know about this. That's going to be the torque of the aluminum. That's one of our unknowns. The length is 25 meters. The J that we have of the aluminum is going to be pi over 32. Now this is the hollow section. So remember, it's got an outer of 72 and an inner of 54. So we have to subtract out the steel. So in this case, remember that we have 72 millimeters. I'm going to write it like this. If it's 72 millimeters, 1, 2, 3. So we have 0.072 to the fourth. That's the outer diameter minus 0.054, the inner diameter to the fourth. So that's our value of J. I've got to keep going on this guy. Divided by the G value of the aluminum. And that's going to be 27. GPA, remember, is 10 to the 9th. So KPA is 10 to the 3rd. M is mega, 10 to the 6th. GPA is 10 to the 9th. You need to know that. So make sure you've got that. All right, so that is the theta in the aluminum section. Theta in the steel, we have the torque in the steel times the length. That's also 25 meters. Now it's the length segment that we have. Divided by the area of the steel, that's pi over 32. Now that's just this. That's just a solid core. So there is no outer minus inner. It's a solid section if we just look at the steel. So that's going to be 0.054 raised to the 4th power. And then we have the G value of the steel, which is 77 times 10 to the 9th. So that is our expression, or that is our statement that we've got then for the stress-strain law. All right, so the next thing that we've got to do then is our last remaining tool of structural mechanics, and that's going to be compatibility. And compatibility, I guess we should call that number C, or letter C. That is going to be what? Think about that for a second. That says that theta of the aluminum is equal to theta of the steel. In other words, if you weld a bar across this thing, everything is fixed. There is a perfect bond there. We don't know what it is, but there's a perfect bond between the steel and the aluminum. That means that if you take a bar across it or a piece of spaghetti and you twist it, it ends up like this. That means they're both rotating the same amount. So the angle of twist is the same for both segments. So what we're going to do is equate these two together. So that is how we're going to solve this problem then. Let's go ahead and redo that. I'll try to leave up enough space. So we've got that the torque in the aluminum times the 25 times pi over 32, 0.072 to the 4th minus 0.054 to the 4th times 27 times 10 to the 9th. That's going to be equal to the theta of the steel. That is torque in the steel times 25 divided by pi over 32, 0.054. By the way, I'm just copying these two. 0.054. And then we've got 77 times 10 to the 9th. There we go. So that is our statement of compatibility. Now notice we haven't gotten rid of any of the unknowns in this case. We still have torque in the aluminum and torque in the steel. This is a little bit different than what we had for the fix bar. So notice we still have both unknowns, but that's okay. Now remember that a lot of times for these statically indeterminate problems, things cancel. So notice the 25 is common. Pi over 32 in the J calculation is common. 10 to the 9th is common. So again, my suggestion or my hint is to save your computations for later. So cancel when possible. So you might want to delay in punching all of your numbers out, and perhaps not. It's not going to do any harm, but you might want to consider going a little bit faster when you do something like that. All right, so if we do this, what happens? Well, we can bring these two upstairs. They can go onto the other side. And here's what we find. We find that the torque in the aluminum is equal to 0.75758 torque of the steel. So what do we do with that? Well, remember, we have 4 is equal to torque in the aluminum plus torque of the steel. So now we just basically take this and it goes in here. So we're going to have 1.75758 torque of the steel is equal to 4. And that allows us then to solve the torque in the steel is equal to 2.276 kilonewton meters, and the torque in the aluminum is equal to 1.724 kilonewton meters. So the steel, notice it takes most of the torque. It's the inner core, and its G value is so much higher that it takes most of the applied torque, although they're relatively close, but still the steel takes the most. And then why is that? Because G of the steel is greater than G of the aluminum by a factor of 3. So now the stress calculation is going to be very straightforward to do. So now we get the stresses, and it's going to be tau is equal to T rho divided by J. But now this is going to be for each segment. So for each part, not the total. We're going to take those values for each segment and punch those numbers out, and we'll do that in the last part for today. But for now, we are done with the third. To the fourth.